So in this video we will be covering a classical Irodov problem. As you can see the question, it is question number 3.28 and I have written the solution and I want to explain you all because it is a very good question and has got a very conceptual point to make. So without any further delay, let's start it. So first of all, let's see what the question says. So question says is inside a ball of radius, so inside a ball charged uniformly with volume charge density rho, there is a spherical cavity and the center of the cavity is displaced with respect to the center of the ball by a distance a. So find the field strength E inside the cavity assuming that the permittivity is equal to unity. So now let's move and yeah, you all can see the diagram I've made here. So this is a sphere of uniform volume charge density. So for solving these questions, I have taken certain assumptions. Assumptions like basically, let me be clear. We all know that we have to find the answer in terms of the given parameters. And the only given parameters in this problem specifically are A and rho. So somehow we have to make or we have to adjust with these two variables only. And we have to find our answer in terms of these two only, right? So as you all can see, I've made this diagram and this is a small cavity as you all can see with center C2 and the center of the spherical and the center is C1 of the ball, right? So what are those assumptions that I've made? I've already listed out here. The center C1 is the center of the sphere, C2 is the center of the cavity and A1 is the vector joining both the centers. I mean the centers of the cavity and the center of the sphere, whereas r dash is the position vector of the point inside the cavity where we have to evaluate the electric field, and this position vector r dash is with respect to the center of the cavity. And similarly this s vector is the vector from c1 to the point inside the cavity where we have to evaluate e. So this diagram, we have made a small cavity and we have made these vectors a, s and r dash. If you're not able to see all that properly, I've made them very clearly here. As you can see, c1 is the center, c2 is the center of the cavity, c1 is the center of the sphere, and r dash represents the position vector from c2 to the point where we have to evaluate the field, and this s vector is the vector from c1 to the point where we have to evaluate field. So we'll use a special approach here, and the approach is the principle of superposition. So what does this principle says, or we can usually find out like, see, we can assume this problem in two parts, mostly like if we have to find electric field at a point inside the cavity, what are we going to do actually? We will first find the electric field due to the entire sphere, okay, having the position vector s. And now we will also take the electric field due to a sphere having negative charge density and having the same dimension as that of the cavity. So when we will sum both of them, we'll get the equivalent or the net electric field at a point inside the cavity. So we all know like the electric field. Firstly, the electric field inside any point in a solid sphere is rho s vector upon 3 epsilon naught. This is very clear to all of us. And similarly, electric field due to a sphere having negative volume charge density, and we have to find electric field at any point inside that. So for a point that is at a position vector r dash inside the cavity, we will use this formula minus rho upon 3 epsilon naught r dash. So the net field becomes rho upon 3 epsilon naught minus s vector upon s vector minus r dash vector. So I hope this much is clear till now. And now this s vector, seeing factorially, we can write s vector as r vector plus a vector. So this r vector plus a vector can be is equivalent to s vector. So that is what we wrote in the next line, and we got a vector plus r vector minus r dash vector. So both the r dash vector will cancel one another and we will be left with rho a vector upon 3 epsilon naught. This is the net electric field at any point inside the cavity, right? This is in the vectorial form, and if we want to consider the magnitude, so this is the magnitude, that is rho a upon 3 epsilon naught. So from this question, people, we can make a very good, or we can get a very good conclusion that if we are about to find electric field inside a cavity at any point inside the cavity, then the field does not depends upon the dimension, or I would say the size of the cavity. It just only depends on two factors, and the fact only one factor, and that factor is the distance between the axis of both the spheres, or I would say the distance between their respective centers. So here the distance between the respective center was A. So we somehow managed using our concepts to find the electric field at any point inside the cavity, and that came out to be rho A upon 3 epsilon naught. So I hope this will be helpful to you. And yeah, and if you find this content really amazing or good, all you can do is like, share, and subscribe. Thank you everyone. Until we see meet next time.